you still see most of the stuff you need to?
If I need to, I'll just scoot over.
Okay. There we go. Now let's pause it. I need to start doing this for each of my recordings. So in case there's any question. Let's see, we're chapter 7. This is on 6:13. Here we go. Well, let's get started on chapter 7.
It shows when you have a small class, I guess.
Yeah, I mean, it doesn't take many to decimate the class. All right, so last time we met, we covered chapter 6, chemical reactions, and now we're going to focus on chemical reactions, particularly in aqueous solutions. Here we go. All right, reactions don't just happen. Chemical reactions have a driving force, something that makes them happen. And at this level, or at the beginning, we're going to take a qualitative approach, which just means, can we observe something about the reaction that indicates what is driving it? We can categorize the driving forces into 4 groups. If you say put 2 solutions together, and that means you can see through them, they're clear, and they get cloudy when you combine them, then you've formed a solid. We call it a precipitate. If that forms, what's happening is, say you have this component that's aqueous and this component that's aqueous. Then if you form some other component that's a solid, what that tends to do is it takes this, whatever was required from this side, forming a solid, and the solid drops out of solution, effectively removing it from the reaction medium. So when you pull this away, it just tends to pull the rest of it with it. We can make a similar argument for the formation of water. Whenever you form water from 2 aqueous solutions, we mark it as a liquid. Whenever you form water, this becomes part of the solvent. So while it is possible to reverse the reaction, generally speaking, if you form water, that is also going to be a driving force for the reaction. If there is a transfer of electrons, electrons are transferred because they want to be someplace else. Right? So if you have say solid sodium and chlorine gas, and you combine them, you can get sodium chloride, which is a solid. Now, granted, that's not in a solution yet, but if you try to put sodium in a solution, you can't get that reaction. because sodium so violently reacts with water. That in itself is an argument for this reaction where you, well, no, not where you form water. It reacts with water. But in the process, it's also transferring electrons, right? So this is going to transfer electrons to chlorine. Chlorine wants to gain electrons because if chlorine can gain one electron, it looks like argon. It isn't argon, of course, but it looks like it electronically. Sodium, however, if it loses one electron, then it looks like neon. And generally speaking, particularly the representative elements, these two and all of these, they tend toward the appearance, electronic appearance of noble gases. And that's behind this transfer of electrons, is the tendency toward noble gas configuration. So when you do that, you give them the opportunity to look like their nearest noble gas. Now that's not balanced, of course. We want to be consistent. There we go, now we're balanced. Okay, so that's formation of solid, formation of water, transfer of electrons, and the formation of a gas. We can use a similar argument for the formation of gas as we did for the formation of a solid. When you form a gas, it tends to bubble out of the solution and it's removed from the environment. And that tends to pull the reaction toward the side that gives you the gas. I think we've got I've got a little video here. Might have to start it manually. There it goes. Oh. Sound.
It's because we get a change of color. There are lots of other ways that a chemical reaction can show up. And one way is called a check.
Start again.
So in the reactions we've seen so far then, we mix chemicals together and we know that a reaction has taken place because we get a change of color. There are lots of other ways that a chemical reaction can show up. And one way is called a change of state. So the state of something just means whether it's a solid or liquid or a gas. So if something turns from a solid to a liquid or from a gas to a solid, then it's changed state. So let me show you an example of a chemical reaction that involves a change of state. So I'm going to use these two liquids. I have a red liquid and a colorless liquid. What I'm going to do is to pour the colorless liquid onto the red liquid very carefully and try to make two layers. So what I want to happen is for the colorless liquid to be floating on top of the red liquid in separate layers so they don't mix. It's worked quite well.
Let me think.
So what I've got now is one liquid floating on top of another, and where they meet,
he's
they undergo
okay
a chemical reaction. They're actually making a solid. A solid material is formed with the two liquids meet. What I can do is to fetch out some of this solid material. And as I pull it out of the beaker, of course, it allows the two liquids to meet each other again, and so they react again to form more of this solid. So if I'm careful, so as I wind, I'm pulling up this material, and it allows the two liquids to meet again, and it forms more of this material. And this substance that's being formed is actually nylon. So we're making nylon as I speak. And if I'm careful, I'll be able to just keep on turning this and making this long thread of nylon, at least until we run out of solutions. Okay, so that's an example then of a chemical reaction that involves a change of state. So let's have a look at another reaction that involves a change of state. And for this, I'd like a volunteer, please. Who would like to volunteer? You're very keen. Come on down. Let's have a big hand for a volunteer. You would like to stand there. Let's pop those on. What's your name? Dylan. Right, Dylan, if you stand just there, we're going to do some chemistry and we're going to make it a solid. Right? I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. When I add the ammonia, you see that it's forming a sort of brown colour. I'm going to keep on adding the ammonia. In a minute, that brown colour should disappear. Maybe that's disappeared, isn't it? Now what I'm going to do is add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So now I'm going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. This takes a moment or two. There we go. And then finally, I'm going to add some glucose. So there's the glucose. Now I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan. I want you to hold that. Now just give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place, and it's forming a solid. And the actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour, is that okay? It does actually take a minute to do, but the harder you shake, the better it works, so keep shaking, don't drop it then. So metal, silver metal is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal in the sort of a mirror building up on the inside of the flask. And you're all seeing those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. Little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, so have a quick look. Almost there, keep going a little bit longer. Still looking a little bit dark. Excellent. All right, go back to me then. Right, we're going to take the clip off. Take out the stopper. Just wash that off. And we'll pour out the remaining chemicals. And then I'm going to rinse this out with distilled water. Rinse it out a second time. Rinse it out a third time. There we go. And just look at the that on, dry this off. And put the clip back on. And if you'd like to just give that a little polish, if you'd like to hold it up by the neck, that's it. And if we bring a camera in, have a look at this, and we've got a lovely silver mirror. There we go. Stand there. Okay, what we're going to do is give that to you as a souvenir to take home, and you can go back to a thing. Let's have a handful on the floor. Okay, so that's an example of a chemical reaction that produces a change of state. I want to show you another example of a chemical reaction. Again, this is going to go from being a liquid to being a solid. So in this flask, I have a solution of sodium acetate. And this sodium acetate is a liquid, as you can see, but it would very much like to be a solid. It would like to turn into a crystal. It needs a sort of an excuse to get going. And the excuse is going to be some little crystals of solid sodium acetate in this dish. So watch what happens. I pour the liquid onto the crystals. I think you can see there, the liquid, as soon as it touches the crystals, it's turning into a solid. And with a bit of luck, we can make a sort of chemical sculpture. Seems to be working. Okay, so that's a sort of sodium acetate sculpture. funnily enough, this actually has a practical application. This is the practical application. This is something called a hand warmer, and it's a plastic pouch, and it contains exactly the same liquid as in this flask. It's a solution of sodium acetate, and it would like to turn into a solid, like to turn into a crystal, but it needs an excuse to get going. And the excuse is this little metal disc, and if I just flip this disc backwards and forwards, that should be enough just to start the crystallization off, and there it is. We can see the liquid turning into a solid. And as it does so, it's actually getting warm. So it's actually giving off heat. And there it is, it's turned entirely into crystals. It's become quite warm in the process. I can put that inside my glove and keep my hand warm for half an hour or so. And then I can take this and put it into boiling water for a couple of minutes. The crystals will turn back into a liquid. I can allow it to cool, and they'll stay as a liquid, and they'll stay like that for weeks or months until I'm ready to use it again. You can use it thousands of times. Okay, so that's sodium acetate, a sort of chemical sculpture. I'm going to show you now another way to make a chemical sculpture. And Chris has been preparing this. This beaker contains a mixture of para-nitroacetanilide and sulfuric acid. And Chris has been warming it up. And when it's hot enough, it will undergo a reaction in which this liquid will turn into a solid. This makes quite a bit of smoke, so we've got this special hood that will suck away the smoke from the reaction. Here it goes. Okay, so that's the chemical reaction that involves a change of state. So
You can do that reaction with table sugar, concentrated sulfuric acid.
How do you get sulfuric acid?
It's not easy.
That's what I was about to say.
That comes in the lab kits.
Possibly, but there's not much of it in there. What it does is it takes the sugar molecule and dehydrates it. It extracts water from the sugar molecule, and the only thing that's left is carbon. So you get that that black chimney.
Yeah.
Carbon formed from it. Okay, so that was just a demonstration of chemical reactions. And if you go back and look at this Zoom video later, the quality probably won't be very good, but you also have access to the PowerPoint. And the PowerPoint slides, when you view that on your computer screen, they'll look fine. Okay, let me take control of this again. There we go. All right. So, there was a lot more to that video than I showed you, but it goes on for like 20 or 30 minutes.
I'm gonna drop that silver knife. That silver.
Oh, yeah.
I mean, my hand was slipping. Whoops.
That would have been a disaster.
Yes.
Okay, so when we form a solid out of two liquids, we're conducting a reaction that precipitates. It's a precipitation reaction. The solid is called a precipitate. And here's another video.
What I have here is two thermometer flasks. One has lead nitrate solids in the bottom, and one has potassium iodide solid, or salt in the bottom. I'm going to make a solution, an aqueous solution with these. So I'm going to make aqueous lead nitrate here. Mix in. You can see that it makes a solution. And it does dissolve. It is definitely aqueous. And same thing with the potassium iodide. Hopefully I don't make as much of a mess. So the Ki, adding some water, also make an aqueous solution. And both of these solutions Both these salts are soluble in water. So I stir, and I have two aqueous solutions. You can see through them, and you can see the solids are now been dissolved. Okay. Now, interesting enough, lead nitrate is made of the nitrate ion. The nitrate ion is NO3-1, and anything combined with the nitrate ion is soluble because the nitrate ion, NO3, is 4 atoms stretched, and you have a negative 1 stretched over 4 atoms, so its charge density is very low. So it doesn't attract other ions in a crystal as strong as others. So its lattice energy is lower, and it's easy for water to pull apart the ion and have those molecular ion attractions that make this a possibility. Same with Ki. You have potassium iodide, you have Ki ions that are free, this aqueous solution, and the K is +1. The +1 ions are a big ion, and they are spectators for most types of reactions because they have a +1 over a large area as well. And the iodine, like most halides, are also soluble because they're a -1. It's also a big ion. There's some exceptions with those, and you're going to see that one right here. So I'm going to pour these together and take two aqueous solutions and see if a precipitate results. Now, precipitate is when a solid comes out of the solution because we're going to do a double replacement of something called a metathesis reaction. Lead +2 from this beaker is going to attract and hook up with the iodine ion to make PbI2 or lead-2 iodide. And that is going to create a precipitate because the lead iodine prefers itself more or attract itself more than water. So let's do that. Here we go. Very brilliant reaction. You see that pretty, very pretty yellow precipitates. A lot of yellow lead paints have been known to be yellow. And also a problem. So there you go, there's a precipitate. And it's a precipitate because I know that I cannot see through the solution anymore. And if we let this settle for a while, we'll get something like this. This is a reaction I did about an hour or so ago. And you can see here that the clear solution is the potassium nitrate ions, so potassium and nitrate ions, and the solids are at the bottom. That's settled at the bottom. All right, so there is your precipitating reaction.
Okay. So that's the reaction that's actually taking place. The lead nitrate is a 2+ ion, and nitrate is a -1, so you need 2 of them. And the potassium and iodine are both 1+ and 1-. The potassium nitrate will form a solution, is soluble, but the lead iodide is not soluble. It forms a solid. Now, how do we know that? If you look in your review document at the very back, there's that chart with all the white and gray squares. And all you have to do is look at the ion, the cation across the top, positive ions, the negative ions down the left-hand side, and just follow them where they meet. And if it's clear, then they're soluble. If there's a gray box there, then it's insoluble. Okay, so there was the formation of a solid which drove that reaction.
What I have here is 2 elements.
Go to the next slide. Okay. All right, so this chapter is primarily about aqueous solutions. So an aqueous solution, of course, will be one in which the solvent is water, and the solute, that which is dissolved in the solute, is something else. So we need to know something about water. How does water work? What characteristics define water as a solvent? And it's often described as a universal solvent, which is kind of stretching it a bit because there's nothing that can dissolve everything. But water is pretty good at dissolving a lot of things. The water molecule is what we call polar. And the best way to think of polar molecules is that they have one end is positive and the other end is negative. Not completely negative, not the same as an ion. An ion requires a complete transfer of electrons from one place to the other, or one atom to the other. But a polar molecule only needs a slight redistribution of electron density so that you get a slight negative on one side and a slight positive on the other. What that allows it to do is attract itself to ions and other polar molecules. So since water is a polar molecule, and it looks like this, there's your oxygen and your H2s, two hydrogens. As it turns out, oxygen is a stronger attractor for electrons than hydrogen is. Right? So the electrons that are contained in this bond, and whenever we have a single line, that means two electrons in that bond, the electrons are attracted toward oxygen, and we use a symbol like that, an arrow with a plus sign on this end to show you that this is slightly positive. And that's what that little Greek letter delta means, slight positive. And slight positive over here for the same reason. Okay, so that means this end is going to be a slight negative. And we'll use a 2 there just to make sure things balance. Okay, now if this molecule, if the water molecule were built like this, then those slight differences would cancel one another out, right? But it's not. It has a bent structure, which means in physical terms that the resultant or the combination of these two arrows is one that generally is in that direction. Right? So this molecule is going to be slightly negative on that side, slightly positive on this side. And when it encounters other water molecules, so you have pure water, then it's going to align itself like that and form a slight attraction between this positive side and that negative side. Okay, this has a special name. That's a hydrogen bond, but it's a special kind of dipole bonding. So you have a dipole here and a dipole there, and they attract one another. But when you have a hydrogen involved with an electronegative, we say, atom, you have the potential for hydrogen bonding. Okay, so there you go with your polar molecule. Remember, if water were linear, it would be a nonpolar molecule because those arrows would cancel one another out. So a great many things in the universe are either charged or polar. So that's why we say water is a universal solvent, because most of the things that it comes into contact with are polar or ionic, and it can dissolve them fairly well. There are, of course, there are a whole host of molecules that are not polar. And in that case, water doesn't dissolve them to any significant degree. Okay, Here's how water dissolves an ionic solid. This is sodium chloride. And like all ionic solids, this may be the simplest ratio of sodium to chlorine, which is 1:1. But in the structure of the salt matrix, you have all these ions together, right? So you don't have a discrete molecule of sodium and chlorine in this case. You just have an array of sodium and chlorine ions. So how does water attack them? Okay, notice that sodium is positive charge, chlorine's minus charge. So when water approaches, if it encounters a sodium, it's going to orient itself so that the negative side of the molecule is against the sodium. And the positive sides are sticking out, and they're still attracted to other water molecules, right? So there's a pull on that sodium. And once you get enough water molecules associated with that sodium, they will pull that sodium ion away from the crystal. Now it's in solution. It's what we say, it's hydrated. Similarly, the chlorine, when they're exposed, the positive side of the molecule becomes oriented to chlorine, and a similar effect occurs where the chlorine ions are pulled into solution. And this just keeps going until one of two different things happens. Trying to go backwards. It's not going to let me. One of two things will happen when you put a solid in water. Either the entire solid will be dissolved, it'll just disappear into solution. Or at some point, you may reach a point where the solution can hold no more of the solid in solution. And at that point, the solution is what we call saturated. You can't put any more in. Okay, so if you have an ionic solid dissolving in water, one way to verify that what you have dissolved in water is ionic is to test it to see if it will conduct electricity. If the solution will conduct electricity, then the solute that you put into solution is ionic, or at least polar. The more current that you can transmit through the water, the more likely it is to be ionic. So you get a lit light bulb if you have free ions floating in water. That's just so the charge can be transferred from one electrode to the other and complete the circuit. Pure water is an insulator. It will not conduct electricity at low voltage. The only way you can get water to conduct electricity is to crank the voltage up very high, thousands of volts. If you do that, then what you're doing is you're going to split the water molecule into hydrogen and hydroxyl ions, and then it will conduct electricity. So that's why they tell you, if a thunderstorm rolls through, get out of the tub, right? Because there's plenty of voltage in a lightning strike that will ionize the water, and it'll go straight through you into the ground. Well, she wasn't a friend of mine, but a classmate when I was in high school was talking on the telephone, and that was back in the days when all telephones were landlines. But she was in the tub while she was doing it. Thunderstorm rolled through, struck the telephone line, went right down through her into the floor, and she was dead. So water will conduct if the voltage is high enough. But for low voltage, water is an insulator because there are no free ions to conduct enough electricity to light the bulb. Now, we have a name for those. It's called electrolyte. Doctors talk about electrolytes all the time, right? When they send your blood away or your urine away for analysis, one of the tests they do is electrolytes. They'll test for the various ions that are contained in the solution such as sodium, potassium, chloride, some others. But those together are classed as electrolytes, and they will allow the solution to conduct electricity. A strong electrolyte is one in which the substance that you're putting in solution, the solute, will completely break apart in solution. Strong electrolyte. Sodium chloride is an example of that. Let's see. Let me back up. The reason I want to back up is there was more to that story, and I'm surprised that the slide doesn't contain more of the story. I have to do it manually. Okay, so let's get started again on this slide. Here we go. A strong electrolyte will completely dissolve all the ions in water and form a good conductor. A weak electrolyte is one that only very slightly dissociates. Okay, an example of that would be, say, acetic acid. If you put acetic acid in water, then what it does is it breaks apart into protons. That makes it an acid. And the acetate ion. But it only does so very slightly. Most of it stays back over here. That means it's not conducting. So that's a weak electrolyte because it only forms just a few ions. And if you put the same amount of acetic acid in solution as you do molar-wise, the same number of moles of acetic acid in water, a certain amount of water, as you do sodium chloride, you'll find that the sodium chloride will light the bulb very strongly, but the acetic acid at that concentration will only be a weakly lit bulb. Okay, so now we can go to the next slide. I thought that was important enough to stop and add to the conversation. So these compounds are aqueous, that is, they go into solution very easily. Potassium chromate, recognize the polyatomic ion, right? We have 3 or more atoms in that compound, and one of them's oxygen, so we suspect polyatomic, and in fact it is, potassium chromate. This one is barium nitrate, okay? All nitrates are soluble. So we put those in solution, and they're in separate solutions to begin with. The ions separate from one another, go into solution, so those would be strong electrolytes. Now, what happens when we put them together? Well, we get the potential for a double replacement reaction, right? You can have potassium now could associate with the nitrate, right? The cation with an anion. And the cation from this one, the barium, could associate with the chromate ion. So if we let them do that, we have these possibilities. Well, potassium nitrate, we've already, let's see, potassium chromate is one that we put in solution, and barium nitrate we put in solution. And then the other possibilities are this combination and that combination. So what happens? Well, the potassium and the nitrate are soluble. All nitrates are soluble. All alkali metals are soluble. So you get a double whammy there. It's definitely soluble. But the barium and the chromate, when you put those together and you look it up in your chart, you find that barium and chromate together make a solid. So our two reactants together, while potassium nitrate, when it's not in solution, is a white solid. Barium chromate, when it's not in solution, is a yellow solid. When you put this in solution, put that in water, it goes into solution, stays there. But barium chromate is not soluble. So when you put those two solutions together, you form the barium chromate, kind of like that previous lead iodide formed that nice yellow color. You get a yellow color out of this one too, barium chromate, primarily from the chromium. That's where the yellow color comes from. Okay, these are the rules for solubility. You'll find them at the bottom of that page with a block diagram. Okay, they're just there for you if you're interested. We don't have enough time, and this course isn't designed for producing world-class chemists. We just want to give you enough information so that you can go to the next step. So that's why I've incorporated the table. Just learn how to use that table, and you can find out. If you do it enough, these rules just sort of imprint themselves on your mind. The first rule is that nitrates are all soluble. The second rule, that sodium, potassium, and ammonium salts are soluble. Most of them. Third rule, most chloride salts are soluble, with these exceptions: silver, lead, and mercury 1. Those are all insoluble. Sulfates are generally soluble, with these exceptions: barium, lead 2, calcium. They're insoluble. So those are exceptions to the rules. Most hydroxide compounds are only slightly soluble. So for the most part, they are considered to be insoluble. But this is a good time to make that comment. Solubility is on a continuum. You can say something is insoluble or it's soluble, but in fact, it's somewhere in between. Now, sodium chloride, potassium nitrate, all the nitrates, they're definitely down here on this end. They're all soluble, 100%. Except when you put too much in there, then you saturate the solution. In fact, I've got a bottle sitting in the lab now that we used yesterday in my Gen Chem 2 lab. It's saturated sodium chloride. So you can saturate a solution with table salt. But up to a point, it's soluble. And then down here, you have insoluble compounds. There are some that are so insoluble as to be the amount of ions formed in water are insignificant. But others fall very close to insoluble, but some of them, there's a little bit of them that goes into solution, very small amount, but it can be measured. So this is your continuum of solubility. When we say insoluble and soluble, those are generalizations. Most sulfides, carbonates, phosphates are only slightly soluble, or we might consider them insoluble. Right? So calcium carbonate, right? You ever go down in caves, the stalactites and the stalagmites, they're formed from calcium carbonate over centuries. It takes a long time.
Well, I've been to, it was around in here in West Virginia. Maybe just took everybody those caves that it might be that there's real pretty rocks in them.
Lewisburg.
Yeah, yeah. What
Yeah.
form do those crystals look things inside those rocks? What form is that?
Well, most of them are made from calcium carbonate,
Is it?
but they can have some other inclusions in there, different minerals.
They're beautiful.
Yeah, and the slower you form a crystal, the more perfect and larger the crystal is. You have fewer imperfections. Okay, phosphates are generally insoluble. Sulfides also. So there's your chart, and these are the rules. The only thing about the rules is, if you have a conflict between two or more rules, the one above takes precedence. Right? So if, say, you have, you're comparing something that involves this rule and this rule, that one wins. Okay, that's the way they're lined up in that order. So the one on top wins. But you just need to learn how to use that chart. Okay, let's see, what are we trying to do here? Solubility rules, predicting precipitates. I think we can, actually, there's just one rule that you need to know. When you put two solutions together, the ones that we're going to look at are involving two ionic solutions, which are formed from soluble compounds. Then when you put them together, you swap the cations with their anions and see what you get. And then you can compare those in your chart, see which one makes a solid. Okay? Usually there's only one solid formed. On rare occasions, you can get two solids formed. So, the beginning procedure is the same as always. You write your reactants correctly. Right? They have to balance your charges. Like if you're given for that earlier one, we had lead 2 nitrate. Right? So you got to be able to take that name and write the compound. So lead is going to be a 2+ charge. And then the nitrate is a polyatomic ion that's always -1. Right? So then to make it balance, since it's polyatomic, you have to use parentheses in 2. So now you've written your compound correctly. You do that for the next one. And then you, let's see, what was the other one? Potassium iodide, wasn't it? And these are both soluble. This is one of those reactions where I won't tell you what the products are, because you should be able to simply do a cation swap, a double replacement. So you just put this one over here, that one over there, and see what you get. So this one over here gives you potassium nitrate. You look it up. Well, all potassium salts are soluble, all nitrates are soluble, so this has got to be soluble. And then you look up lead 2 iodide. So we want to write the compound correctly. Right? Iodine's -1, 2+, so this has to be 2. And you look it up in that chart. Lead across the top, iodine down the side, follow them over. It's like you're reading a mileage map on planning a trip. See how far it is. Well, you follow them over until they meet and see if it's clear or grayed in. In this case, it does form a solid. Now you have your reaction written with reactants and products. Okay? Then you balance the equation. Okay? So you can use You can use our budgeting process, or if you really are comfortable with balancing equations, you can just go in and say, all right, I got 2 nitrates, I need 2 nitrates. That means I got 2 potassiums there, I need 2 here, 2 iodides there, 1 lead, 1 lead, we're balanced. Most of these double replacement reactions like this that form solid are fairly easy to balance, because you've got 2 ions here, 2 ions there, 2 ions there, and 2 that form a solid over here. So they follow a pattern. So they're relatively easy to balance. Okay. So which of the following ions form compounds with lead 2+ that are generally soluble in water? Well, you just take your chart and you find your lead, which is way over on the right-hand side, almost the last one. And then you follow it down and you look at each one. So follow lead down to sulfide, it's insoluble. How about chloride? Lead chloride, follow down to the chlorine. Lead chloride is insoluble. Okay. Lead nitrate, well, you probably don't even have to look that one up, but you can. So we go down to the nitrates. Nitrates is actually at the top, followed across, it's clear. So that one is soluble. Sulfate, go down to the sulfate, which is about midway down the left-hand side, followed across, it's grayed in. It's insoluble. And this one's for people who are not paying attention. You don't have 2 cations together to form a compound. So that one's eliminated right off the bat. So the only one that's soluble is the nitrate. Okay. So let's see how we do on time. We go till 11:30, don't we, or 11:20? Okay. So let's say a sodium phosphate solution reacts with a lead 2 nitrate solution. What precipitate will form? So we have a sodium and a phosphate. Okay. So that's 3-, this is 1+, we need 3 of those. It's aqueous. And then lead 2 nitrate, we did that one before. That's aqueous. The question is simply, what precipitate forms? Right? So what do? You take this one and swap it with that one. So now sodium is combined with nitrate. Is that soluble? Look it up in here. Well, all nitrates are soluble.
Yeah.
And all alkali metals are soluble. So we know that one is. So then we want to check to be sure, is lead 2 phosphate soluble? Well, just for practice, let's write this one correctly. That's 3-, this is 2+. So we just say 2 over here, 3 over here. But for looking up in the chart, you don't need to know that. Just look it up in the table, follow the lead across, go down till you meet the phosphate and see if it's soluble or not, if this is gradient square. It's not soluble? Okay, so there's our solid. Lead 2 phosphate. I don't have no paper.
Oh.
I have it at the house, I don't have it.
See if I got it.
It's okay, you don't have to waste your time, I'll watch the video again.
Okay. So what if we just give you a whole set of ions in solution? Can you figure out what different solids are possible? There are a couple of ways you can do this. You know, if you're good with with forming arrays in your head, that's fine. But if you want to do this methodically, then you take the cations, pull out the cations, and put them down. Let's be consistent, our charges across the top. So we put lead 2 plus, and then potassium, and then silver. Those are all the cations in that list, right? So then down this side, we'll put the nitrates and the chlorides, the sulfates, and the phosphates. Just make ourselves a grid. And see which ones are soluble. Well, that's soluble, and that's soluble, right? Because they're all nitrates. Potassium, all potassium salts are soluble, right? So we can get rid of those right off the bat. Then we can go look in our chart and say, all right, so let's take lead 2 plus. Lead 2 plus and chlorine is insoluble. Okay? Lead 2 plus and sulfate. That's insoluble. And I bet phosphate is insoluble also. Sure enough, phosphate is insoluble. Then we can go over to the silver, find out where silver is across here. It's about a little past halfway. You follow it down until you find the chloride, insoluble. How about sulfate? Follow it down to sulfate. It's insoluble. And phosphate. Silver down to phosphate. It's insoluble. Okay, so we've got, these are the possible precipitates that would form from that mixture of ions in solution. Okay? Now it says 5 different solids, but according to our chart, there's 6. All right, let's see which one's missing. They're saying this one, okay, that one's okay. This one, and that one. So they got all the leads agree with us. Silver chloride, they agree with that one, and silver phosphate, they agree with that one. They're saying silver sulfate is soluble. Well, let's see if there's a note in here. Silver sulfate. No. They might be following the rules rather than our chart. That's possible. For sulfates. There's a sulfite. Okay. So I guess the moral of that story is it depends on who you ask. Some of them are unmistakably, like silver chloride, that's going to form a solid, no questions asked. In fact, I used that test, silver chloride test. I built this little kit when I was doing a lot of field work. We'd go out and meet with county agents. Sometimes they'd want to test the water because rice farms. This was in Louisiana. So rice farmers want to know, what's the salt load in their water? Because if they put that water on their field for their rice, year after year, eventually it's going to salt out their soil and then they can't grow anything in it, right? So they want to know what the salt level is. Well, I used the reaction of silver nitrate, and chlorine for the chlorine in the water, because most of it is sodium chloride anyway. So we test for the chloride. And I built this little test And it's reasonably sensitive. You can see the white precipitate form, silver chloride, at a certain concentration, but I wanted to bring the concentration down lower so I could see it. So I used a color agent that would react to silver chloride as it formed. So it would turn kind of an orange. And then I had a little chart in here, you know, how strong is the orange color, and I compare it and give them a pretty good estimate as to what their salt load was. That does some conversions, some mathematical conversions. Say, if my test shows this, then that converts to this load per gallon per acre. So that's a practical application. I don't know whatever happened to that kit. I think it probably got so old I just threw it away. But I still got the book that I used to develop it. Right. Silver chloride, that part forming silver chloride is fairly easy. The part that I needed help with was, you know, what kind of coloring agent would work best, indicator. Okay. All right. So here's another skill set that you need to master. One is, now, when we say molecular equation, we understand that ionic solids and those compounds that are in solution are not molecules. That is, they do not hold together and resist separation in aqueous solution. Right? They're separate ions. So if they go into solution, they're going to be separate ions. But for convenience, we write them as molecules. Right? The whole number ratio, like 2 potassiums for every chromate, or one barium for every 2 nitrates. And then we have barium and chromate 1-to-1 and potassium nitrate 1-to-1. We write them that way because it's easier to balance the equations if we write them that way. So that's where we start. We write the molecular equation and balance it. In this case, we've balanced it, and all that's required is a 2 in front of the potassium nitrate. That gives us 2 potassiums, 2 there, 1 chromate, 1 barium, and 2 nitrates, 2 nitrates. So that's balanced. That's our molecular equation. Now, we're going to slide into reality, and we're going to break up this equation into its components. So let me write the molecular equation up here as potassium chromate in solution and barium nitrate barium is an alkaline earth. It's a +2 charge. Oops, it's not plus, it's yields. And barium chromate is our solid. Yep, sorry, my mistake. Chromate is a 2+ charge. Okay, that's our solid. And then we have potassium nitrate is still in solution. Okay. Now, the reality is, in solution, these guys are ions. So we're going to start off with a complete ionic equation. So we're going to bust it apart into its ions, and these ions are in solution. They're hydrated. So we have 2 potassium ions in solution. Okay? We have 1 chromate in solution. We have 1 barium in solution. And we have 2 nitrates in solution for our reaction. That's actually what you see in solution. But over here, this solid forms. It is not broken apart in solution as an ionic. It is an ionic solid, that's true. But it's a solid, so we write it as one unit. Then we have two potassiums. I have to write them down here. They run out of room. And two nitrates. Okay? So that's our complete ionic equation. We balance the molecular equation, and then we break it apart into its component ions. Two there, one there, one there, two here. Solid, solid stays a solid. Two potassiums, two nitrates. And if you want to check yourself, you say, all right, we've got two potassiums over here. How many we got on that side? Two potassium. We got one chromate over here. We got a chromate here in the solid. A barium there, one there, one there. Two nitrates here, two nitrates there. So we're still balanced. Now, notice that on this side you have two potassium ions, and on that side you got two potassium ions. And on this side you have two nitrate ions, and on that side you have two nitrate ions. They're the same on both sides, right? No reaction. They're called spectators. They just sit there and watch. So if we eliminate those from the equation, we have a net ionic equation. So we can cancel this one with that one, and that one with this one. And now the net ionic equation becomes chromate, ion, barium ion, produces the solid. Oops. That's big zero, big O. Solid. That's our net ionic equation. Okay? That focuses in on the actual reaction, what's happening. You're forming a solid from these two ions. Doors banging. That's what it sounded like to me. Now, what's the advantage of this? Well, it gets rid of a lot of clutter, for one thing. The other thing is a practical matter. If you go into the lab and you want to form this solid from chromate and barium, but you don't have potassium chromate on your shelf, and you need the chromate ion right now, but you do have sodium chromate. Substitute sodium chromate in there, you still got your chromates. As long as the sodium is soluble with nitrate, and it is, you can use that. Or suppose you don't have barium nitrate, suppose you have barium acetate on your shelf. You can use that one because sodium acetate is soluble, right? So there's still spectators. As long as you can mix two solubles together and get the one insoluble and still have this insoluble, then this equation still defines your reaction. So that's a practical benefit to using a net ionic equation. Okay, I think the rest of this slide will show you just what I did. All right. There's your complete ionic with the spectator ions, and this is your net ionic equation. Okay. There should be several examples of that in your review document for you to practice with.
That's the reason I like that scene gauge, because it lets you practice throughout the chapter. And each page uses like simple problems.
Mm-hmm.
Then helps you work them out and tells you what to do. So,
Have you run across these already?
no,
Not yet.
not yet, no.
Okay.
I'm just gonna be honest with you.
Okay.
I'll be in Lord of Mercy. I've been booked this weekend. I got sick.
Yeah.
My wife and son is still sick.
Do they have to go to the doctor?
Yeah. Put them on penicillin.
Okay. Let me see where we are so I don't run out of time. Let's see, 10:45, 11:20. Okay. I think we're going to be okay.
This is going on chapter 7 and 8.
No, 6 and 7.
6.
We already did chapter 8.
Y'all know we know the chapter 6 at that.
Yeah.
Oh.
Yeah. The video should be on Blackboard. We went over chapter 6 right after the exam.
Yeah.
Let's see. Do I have an exam for you yet?
Oh,
Yeah.
yeah, I took it.
Okay.
I mean, I was sick that day I left.
Yeah.
I didn't know that, how far you got there.
That's right. You took it first and then okay. I remember now. Okay. So if we're going to write a molecular, complete ionic, and net ionic equation for the reaction of cobalt-2 chloride, sodium hydroxide, we have to write the compounds first. Cobalt-2 chloride. So cobalt, and it's a 2+, and then chloride is a 1-, so that means we need 2 there. And then we're going to react it with sodium hydroxide. Sodium, and then hydroxide is OH-. So that's a -1 + 1. It's good, just like that. Now, how do we form the products? We just combine sodium with chlorine. Is our first. Of course, we know that's aqueous. And then we combine cobalt with hydroxide. This is still 2+, and that's still 1-, so we need 2 of them. And that, if you look it up, is a solid. So now that we've got the molecular equation, we need to balance it. Because if you don't balance it first, then you can't write the subsequent equations, the ionics and so forth. So we got 1 cobalt here, 1 cobalt there. We got 2 chlorides here. We need 2 chlorides here. But that gives us 2 sodiums. So we have 2 sodiums here. And 2 hydroxyls, 2 hydroxyls. We're good. So now we want to write the complete ionic equation. So this is an aqueous solution. That means cobalt 2+ is aqueous, 1 of them. We have 2 chlorides because of that subscript. We have 2 sodiums. And we have 2 hydroxyls. Because this 2 means 2 of those and 2 of those, right? It's 2 of that entire formula unit. Okay. So now on this side, we have 2 sodiums, still an aqueous solution. And we have 2 chlorides, still an aqueous solution. And we have our solid. Okay, there's our complete ionic equation. Now we look for the things that are the same on both sides. Those are our spectators. Cobalt's in the solid, so we've got to keep it. Chloride, chloride. And sodium, sodium. And hydroxyl, hydroxyl's in the solid, so we keep it. So now we can write the net ionic equation. We got the cobalt, aqueous solution. We've got hydroxyls, yields the solid. And that's our net ion equation. Okay. Now, solutions. Those were solutions where we had electrolytes. Right? Now we're going to talk about solutions where we have acids and bases. What happens to them in solution? The first scientific attempt to describe acids and bases, all we've done so far is that one slide on another slide on forming the equations. Now we're on acids and bases. Arrhenius proposed that acids were any compounds that in aqueous solution will produce hydrogen ions, right? So that means a dissociable hydrogen ion has to be present in the molecule before it goes into solution. Hydrogen chloride fits that description. We combine hydrogen chloride with water, we get protons and the counter ion chloride left over. Okay. Nitrate, nitric acid, hydrogen nitrate forms nitric acid, or H plus and NO3 minus in solution. So that one fits. And sulfuric acid similarly. What did he say about bases? Oh, well, let's get our definitions down. Strong acids are those in which all of the molecules that go into solution dissociate. Like hydrogen chloride in solution will dissociate into hydrogen protons and chloride ions. That's a strong acid. A weak acid is like the acetic acid that I showed you earlier. It only partially dissociates. Okay, so strong acids behave as strong electrolytes because they will conduct electricity very well in solution. Bases. Arrhenius said that bases are those molecules that when they go into solution dissociate to produce hydroxyl ions. Sodium hydroxide is an example. Potassium hydroxide does also. Even barium hydroxide, calcium hydroxide are bases. They're very weak bases because they only partially dissociate. Right? They're generally insoluble, but they do produce a few hydroxyl ions. That's Arrhenius' definition. Now, when we put an Arrhenius acid and an Arrhenius base together, okay, this is often the way you'll see it. We want to focus on the hydrogen ion. So we just say, all right, the hydrogen is associated with some other anion. We call it A for acid. And then for the base, we say something with a hydroxyl on it, with a B. Okay? So the B is the cation and the A is the anion in aqueous solution. When they react, the A and the B are together, and this is called a salt. In chemical terms, a salt is the reaction of an acid and a base. Plus water. That's the general reaction for all acid-base reactions. The general equation for all acid-base reactions. An acid plus a base makes salt and water. So, assuming this salt is soluble, most of the time they are soluble, not always, but most of the time, then if we write this as a net ionic equation, then this anion and that cation are also over here, anion, cation. We can remove those as spectators, and in that case, the net ionic equation for an acid-base reaction is hydrogen ion plus hydroxyl ion yields water. So all acid-base reactions are net this. Okay. Common strong acids: hydrochloric acid, nitric acid, sulfuric acid. Strong bases, common strong bases are potassium hydroxide, sodium hydroxide, lithium hydroxide should be a strong base too. In fact, lithium hydroxide is, the solid lithium hydroxide went up in the with astronauts.
Really?
Yeah, because if you filter the air through lithium hydroxide, you get a reaction that forms lithium carbonate, and that carbonate is formed from the carbon dioxide that the astronauts were exhaling, and it was scrubbing the air of the carbon dioxide for them. And the reason they use lithium hydroxide rather than sodium hydroxide is because lithium hydroxide is a lot lighter. And every pound you send into space comes at a very high cost.
What was the common strong bases that you said?
Oh, sodium hydroxide and potassium hydroxide. Those are the most common, those two. Okay, let's see. So this is just a concept question. What's the net ionic equation for the reaction of HNO3 and LiOH, lithium hydroxide? It's the same as for every acid-base reaction. Protons plus hydroxyl ions yields water. That's the net ionic for all acid-base reactions. Okay, acid-base reactions. Another type of reaction. Remember when we said the transfer of electrons can be a driving force for a reaction. If electrons are transferred in a reaction, we call that a redox, an oxidation reduction reaction. Oxidation reduction reaction, or redox for short. We don't say ox-red because that just doesn't sound right. So we say redox instead. Yeah. We have to define what oxidation and what reduction are, right, so they make sense. And let's take this reaction where magnesium and oxygen together form magnesium oxide. So we need two of these, two of these. right? 2 of those, 2 of these, and 1 oxygen. This is a redox reaction. Now, where are the electrons starting and where are they ending? That's the key. For bookkeeping purposes, we use a system called oxidation state. Generally speaking, oxidation state is the charge. So the charge on a pure element is 0, right? There's no imbalance in charge. There's no imbalance in charge here either, right? But in the compound, oxygen is a 2- charge, magnesium is a 2+. We know that because -1, -2, -3. +1, +2, +3. Okay? So magnesium is going to have a 2+ charge or a 2+ oxidation state. And how did it get there? Well, if you go from 0 to 2+, you can't do it with protons. You have to do it with electrons, right? So the imbalance is an excess of 2+, and to do that, you have to lose 2 electrons, right? If you lose 2 electrons, then you go from 0 to 2+. Okay? So this is the way I do it. I just draw like that, and we have what here? Loss 2 electrons per magnesium. So for each magnesium, you lost 2 electrons. Now, in an oxidation reduction reaction, you can't have one without the other. The loss of electron is called oxidation. So we had to gain electrons going from there to there. So how many did we gain? Well, we went from a 0 to a 2-. We had to gain 2 electrons per oxygen. And a gain of electrons is called reduction. Now, how do you remember that? Oil rig. Oxidation is loss, reduction is gain. Now, of course, you can't transfer electrons, like transfer 3 electrons in oxidation and only gain 2 electrons in reduction. They have to balance, right? So if we've got 2 electrons per magnesium, but there are 2 magnesiums, then a total of 4 electrons were lost. And for this one, you have 2 oxygens, 2 there, 2 here, 4 electrons were gained. So we're balanced with electrons. That's an oxidation reduction reaction. Now, as a general rule, oxidation reduction reactions occur between metals and nonmetals. And generally, the metal is going to be the one that loses electrons. The non-metal will be the one that gains electrons. There's another way to tell whether you've got an oxidation reduction reaction without actually doing this. You just need to know if the reaction is redox. You look at the reactants and the products, and if you see an element on one side, and that element is part of a compound on the other side, you have an oxidation reduction. Or if it's a part of a compound as a reactant and an element as product, same rule applies. If it's an element on one side and in a compound on the other, you have an oxidation reduction without fail. So if the exam question is, which one's an oxidation reduction? First thing I'd do is look for that clue. If there's no clue there of that nature, then I'd have to go in and tally up the electron transfers. Okay. Any questions? That's redox. Let's see, they're going to give us another one to look at. What are we doing on time? So acid bases, redox reactions.
I think the last one's the transfer of gas, formation of gas.
Formation of gas.
The combustion reaction.
Combustions. Oh, we have synthesis, decomposition. Okay, so I'm going to skip this one. This reaction is thermite, aluminum metal, and iron 3 oxide. It takes a very high temperature to get it started, but once it gets going, it forms a lot of energy and heat. It also forms pure iron. That's why the railroads use thermite to weld their rails together. They'll put the compounds right next to the rails, and then they'll cover them with special kind of sand, and then box them in and stick their igniter in there, set them off, and man, the fireworks are amazing. But it will weld those rails together, and the weld is stronger than the rail. So if the rail breaks, it won't break at the weld. Oh, yeah, sure. Okay. Oxidation reductions, usually a metal-non-metal reaction. Two non-metals can undergo an oxidation reduction reaction. For instance, hydrogen and oxygen yields what? Water. So we need 2 here, 2 here. That's what one of the reactions that pushes the space shuttle into space. Well, when it was active. That's that big old orange tank on the outside was actually 2 tanks inside. One had liquid oxygen, one had liquid hydrogen. And then the rocket engines, they combine these two, and you have an oxidation reduction reaction. Now, you don't have ions formed here because this is a molecular compound. But if we follow the oxidation state form, then this is an element, that's an element, they're both 0. But over here, we give oxygen a 2- oxidation state and hydrogen a +1 oxidation state. So oxygen has gone from here to here. By gaining electrons, it is reduced. And hydrogen has gone from here to here. And by losing electrons, it is oxidized. But we could tell by that little rule I gave you, that's an element, that's an element. They're both in the compound. So that's definitely oxidation reduction. Electrons have been transferred. But they're 2 nonmetals, right? So while a metal reacting with a nonmetal is always an oxidation reduction, sometimes you can have 2 nonmetals with an oxidation reduction reaction. In fact, most of the important reactions in your body are oxidation reduction reactions, especially the ones that produce energy. When you take glucose into your system, or maybe a starch and it's broken down into glucose, and that glucose ends up as carbon dioxide and water. And in the process, electrons are transferred to release energy. Okay, so this is just a restatement of the driving forces of reaction, right? We've talked about forming solid, forming water with acid-base reaction, transfer of electrons, redox. Now how about formation of a gas? there's a solid, acid bases, oxidation reduction, formation of a gas. So if we have, in this case, our example is zinc metal and hydrochloric acid. If we combine zinc metal and hydrochloric acid, we get hydrogen gas and zinc chloride. Take a closer look at that reaction if you can. I know it's small. You got a metal here, an element there, and that element is in a compound over here. This is also an oxidation reduction reaction. Zinc has gone from 0 oxidation state to 2+ oxidation state. So it has been oxidized. Whereas the hydrogen here went from a +1 to a 0. So it gained electrons. It has been reduced. But the reaction is also the formation of a gas. A single replacement reaction. Notice when they say single replacement, this element substitutes in here for that hydrogen and replaces it because it forms that compound over there. Combustion reaction. Combustion reactions are a special type of oxidation reduction. A combustion reaction requires that one of the reactants be elemental oxygen, O2. That is a combustion reaction. But it's also oxidation reduction. So this is a decision tree for a chemical reaction. Well, does it form a precipitate? Okay, it's a precipitation reaction. But it's not an oxidation, and it's not an acid-base reaction. If you have an acid-base together, then you have an acid-base reaction. Or you could have an oxidation reduction reaction, in which case, if there's oxygen involved, free elemental oxygen, not elemental, it's diatomic oxygen, then you have also a combustion reaction. Okay. Now, a lot of these descriptions can fit multiple categories. For instance, this one is a synthesis. You take two simple, in this case, elements, and form a compound. You're synthesizing a compound. Well, if we took that compound and broke it apart, the reverse would be a decomposition reaction. But notice that earlier one, well, I can't get back to it. The earlier one was also a combustion reaction. Combustion? Yes, because oxygen was involved. Oxygen and carbon. The decomposition reaction, this one in reverse would also be a combustion because there's your oxygen. If we go that direction, like I put on the board a minute ago, that would be a combustion reaction. But in this case, we're breaking the water molecule apart into hydrogen and oxygen. That's a decomposition. But both of those are also oxidation reduction reactions, right? Because you've got elements over here, compound on that side. So we can expand that chart a little bit more, and under oxidation reductions, we can have a combustion reaction, we can have synthesis, or a decomposition reaction. So this example says that that reaction is oxidation reduction, it's a synthesis, and it's a combustion reaction. All three of those. We'll take the review document next time we meet, and look at there's a section in here, several pages, with nothing but reaction types. Okay, so you get a lot of practice. And then there's a part back here where you actually have to balance equations. Okay. There's at least one that has a picture. We'll deal with that one. Pictures give students trouble because they're so misleading sometimes. So we'll focus in on that. There are a couple in here that I've marked bonus. The reason they're marked bonus is they slipped in here somehow, but they involve using skills that you haven't developed yet. Right, so I think I see 3 of them. So I wouldn't worry about those unless you may suspect that one of them might appear on the test as a bonus. Then you may want to know how to do it. Okay. All right, we're finished 5 minutes early. How about that?